Okay, here's another transformation. This is my famous sane-dimented transformation, so if you're aware of that model, you have a little insight into what I've done here. But that's not important for what we're going to do right now. We're just looking at how transformations behave and how they map one vector space into another. So you got a vector space V here, a vector space W over here. They're both R2 spaces because the transformation takes vectors of length 2 and gives you vectors of length 2. So we're mapping R2 to R2, or something equivalent. Some space isomorphic to R2 to another space isomorphic to R2. If you know what that means, and you might by the stage in the course. Okay, well, we just can do the calculations. What I want to do is I want to map these four vectors over here. And I'm going to start with 1, 0, and 0, 1. That's clear? If I put 1, 0 here, 0.9, 0.2 times 1, 0 gives us 0.9, and 0.1, 0.8 multiplied by 1, 0 gives us 0.1. So that this vector maps to the vector 0.9, 0.1. Now, we can locate that vector. I'm going to mark unit distances on each axis. And 0.9, 0.1 comes out almost to 1 here. And 0.1 is about here, so this vector 0.9, 0.1 might be represented by this arrow. Well, the vector 0, 1, if I multiply the matrix by 0, 1, I'm going to get 0.2 times the 1 and 0.8 times the 1, which gives me the vector 0.2, 0.8. Okay, so that vector lies about maybe this far out on the x-axis and about this far up on the y-axis. So here's the vector 0.2, 0.8. Now, the way I've drawn this, and I've exaggerated just a little bit, but this vector is clearly shorter than this vector the way I drew it, but was that just my drawing? Well, we can use the Pythagorean theorem to calculate the magnitude of the 0.2, 0.8 vector, and we get the square root of, well, 0.8 squared is 0.64, 0.2 squared is 0.04, adds up to 0.68, and the square root of 0.68, well, the square root of 0.64 is 0.8. The square root of 0.68 is a little more than that. I think it's about 0.83. It's not off by more than a hundredth, I don't think. The point, though, is that clearly the square root of 0.68 is less than the square root of 0.82. So even if these approximations aren't all that accurate, we see that this vector is shorter than this vector. Now that's unlike the rotation transformation that we looked at in the preceding, where all the vectors maintained their length and just rotated through about a 37-degree angle. That didn't happen here. Also, the vectors, even though they changed length, maybe they still rotated through the same angle, but no, because the angle between this vector and this vector is 90 degrees. Very clearly, these don't have a 90-degree angle. You got a 90-degree angle between the y-axis and the x-axis, and these are within that angle. So the angle is clearly less than 90 degrees, so this transformation doesn't preserve angles. Well, what else? Okay, the vector 0.87, 0.5, now I'm not going to talk you through that, I'm just going to say that, well, if we apply the transformation to this, it means we multiply this matrix by this, we get these numbers and they add up to this. And if we apply the transformation by multiplying this matrix by this vector, here's what we get. Okay, well, the vector 0.87, 0.5 therefore goes to the vector 0.883, 0.487. Now, point 883 is almost as, very close to point 9, and point 47 is up here pretty close to 1/2. And if we project out here very lightly, you might not even be able to see these projection lines, but it looks like we're going to get a vector somewhere about here. Okay, if you just sketch that yourself, visualize it, whatever, you see that the x component of this vector is almost as big as the x component of the purple vector. The y component is much bigger than the y component of the purple vector. And the way that balances out, this vector is significantly longer than this vector. And I believe the magnitude of this vector, again using the Pythagorean theorem, you can check my numbers, is about 0.117. Well, 1.17. The image of the 0.5, 0.87 vector is 0.624, 0.746. Okay, well, 0.6 is out here a little more than 1/2, and 0.746 is somewhat more than that, so we get a vector comes out maybe to here. Now I haven't labeled that vector because I've got enough labeling. If I add much more, things are going to start getting cramped up. But this vector is also longer than either of these two vectors. Okay, let's look again at the image of the 0.87, 0.5 vector. It's 0.883, 0.487. The 883 is bigger than the 0.87. The 0.487 is less than the 0.5, which means that this vector is a little further out this way and a little closer to the x-axis than this one is, meaning clearly that the angle of this vector with the x-axis is a little less than the angle of this vector. So this vector gets actually turned a little bit toward the x-axis. Notice that this vector got turned a little away from the x-axis. Now this vector, the 0.5, 0.87, which goes to the vector 0.624, 0.746, the 0.5 goes up to 0.624, the 0.87 goes down to 0.746. So the x component again gets a little bigger, the y component gets a little smaller, meaning that this vector turns toward the x-axis, as does this vector. So these three vectors here all turn a little bit toward the x-axis. This vector here turns a little bit toward the y-axis, meaning that there might be a vector in here someplace that doesn't turn. So I'm going to indicate that maybe there's a vector here along this line that doesn't turn. So I'm going to call this the line of doesn't rotate. Again, this purple vector rotates a little away from the x-axis, also changes its length. This vector rotates toward the x-axis, away from the y-axis toward the x-axis, and changes its length. And it changes the length more than this one does. They both get shorter. We have a couple of vectors here that both get longer, but still turn a little bit toward the x-axis. This one turns a little more than this one turns less. Maybe there's a line here where a vector along this line won't rotate. That's interesting. And it's actually very interesting. It's actually extremely important. We'll see how that works out. Let's just get the idea. Okay. Okay, another thing now is and I'm not going to explain why, although if you map the vector, well, the next vector in this series would be a vector at 37 degrees from the y-axis or 30 degrees from the y-axis. And that vector is going to get shorter. The vectors that you get in this quadrant are all going to get shorter. So we have a vector that gets a little shorter here, but then they get longer and longer, but then they start getting shorter again. As we go around the circle, they're going to get shorter and shorter. At some point, they're going to get as short as they do. And I've drawn this line here, but I'm going to kind of smudge it out. So along some axis here, we're going to get the shortest vectors. And we're going to get the longest vectors out here somewhere. Okay, so if we sketch what happens, the lengths of these vectors are going to kind of act like this. Oh, I'm turning at the wrong point. Okay, and if this is where the longest vectors occur, then not very well drawn. But these vectors, if we do the vectors all the way around the circle here, the way we did for the rotation vectors, make an ellipse. Okay, so if we continued the picture for vectors equally spaced around a unit circle, a circle of radius 1, we would get vectors around this ellipse. And I haven't drawn them very accurately, just giving you the general idea. Now you can easily do this, okay? You can easily calculate all these vectors around here and calculate their images and see how that works out. You can also play around with it, try to find the vector on the unit circle that maps to the that doesn't change direction when you map it. See what happens to its length. Okay. In any case, this is a picture of a different kind of transformation. Clearly not a rotation. It doesn't preserve angles. It doesn't preserve lengths. There are many other types of transformations we can look at. We're going to take these two as, in some way, maybe sort of fundamental. And there's another one that we want to look at, so we'll look at that next.